In this lecture, I'd like to take a moment to stop and talk about kinetic molecular theory, which describes some of the assumptions we have been making as we use the ideal gas law. So remember, we're calling it ideal gas law. That ideal gas piece means that we're thinking about the perfect ideal gas and situation. And with that comes a set of assumptions that are characterized as kinetic molecular theory. It's a way that we need to explain the behavior of gases. And what we observe really matches these assumptions that we have under normal everyday conditions, like you would see in a lab where you weren't in extreme pressures or volumes or anything like that. And so I'm going to walk through each of these. And again, this is the theory that is explaining how our ideal gas law works. And remember, some of the things we notice with the ideal gas law is that it was the same no matter what type of like molecule we were talking about that was in the gas state, right? And so that behavior of gases is the same no matter what the identity of the gas is. And we can make these predictions about temperature and these predictions about pressure. So the assumptions we've been making this whole time and the kind of behavior of the gas that explains why this equation works is these five points right here. So first, it's the assumption that these gas particles are tiny, and they are. Gas particles are super tiny, and if you look at a gas sample, like at atmospheric pressure, most of the space in that gas sample is empty. Like there's nothing there. And that's why gases are so compressible, right? And it doesn't require that much energy to compress them. So we're able to make these predictions about behavior, and we see the same behavior between gases because these particles are tiny and they're nowhere near each other. There's a lot of empty space, and that's most of what a gas is. And then we also, to make this work, gas particles we have to assume are always traveling in a straight line, that they're constantly in motion in random directions until they collide with something and then they go another way. Kind of like a whole bunch of billiard balls scattering and bouncing all over the table. So they're constantly moving, they're not stopping, and they're just moving around, hitting stuff. Also, we're going to assume that the attractions between these particles are negligible. The ideal gas law is going to assume that as these particles travel around, they're not interacting with anything unless they're colliding with it. When they collide, they bounce off. And so that means if two get close to each other but don't collide, they're not necessarily attracted to each other or repelled by one another. Now, those attractions and repulsions that happen between molecules is something that we'll talk about in more detail, especially around solutions and solid states in Chemistry 162. When they come together, they actually can be attracted to one another. And those attractions can be a meaningful amount of force that has to be overcome to separate those two. And so because gas particles are moving so fast and are so tiny and far apart from one another, we find that the attractions between these particles make up a very small component of the behavior because of that. And so we just assume that they are negligible because they pretty much are. We also assume that these collisions are elastic. We see very little energy loss when a particle hits the container wall or another particle and bounces off. And so we assume that there is no energy loss. And if you haven't heard that phrase elastic before, here's what I mean by it. So an elastic collision means that you don't lose energy. And there might be an energy exchange, but that there is no overall loss of energy between the two colliding particles. They hit one another and they bounce off. So I can assume then as a particle hitting a container wall, it comes in with one kinetic energy, hits and leaves with the same kinetic energy. An inelastic collision is when two things collide together and there's a loss of kinetic energy. There's a loss of energy that takes place. So I imagine it's like two cars crashing, crumpling into each other and staying put, right? They're not moving anymore. And so that's not what's happening. We're assuming the elastic version. All right, lastly, we're going to assume as part of our treatment of gases or ideal gas behavior, that the kinetic energy of these particles will be proportional to temperature. That means that the average kinetic energy of a gas particles, because you have all of these gas particles in your sample, will have different kinetic energies, right? Which is really that energy of motion, which could be vibration, or rotation, but it's also translational motion through space. So we assume that the average kinetic energy for the entire sample will be proportional to temperature. If we increase temperature, then the kinetic energy of the particles increase. They have more kinetic energy, so we think of them as moving faster. If we lower the temperature, the kinetic energy of all the particles on average decreases too. We could think of them as moving slower. And so all of these assumptions are how we were able, these are all the backbone of the ideal gas law being the predictive tool that it is.